Okay, good evening, all of you. Welcome to this 13th lecture of refrigeration and air conditioning. Uh, I know most of you they are drained by attending online lectures, and my lecture is last today. But I will try to take the revision, and then I will take some small bits because I wanted to start the numericals. Before numericals, we'll take understand the various cycles in vapor compression. Then in next lecture we can start the numericals because numericals are very important. So we are in first chapter, basic refrigeration cycle. In last few lectures we have seen about vapor compression refrigeration cycle, and in last lecture I have showed you the various components involved in VCC. So last lecture we have seen different types of evaporators, condensers, and compressors. And also I showed you how to select a compressor. Like if you go to buy the compressor, then there are some specifications in it. Okay, so they will ask you for voltage, frequency, and single phase, three phase, or different types are there: reciprocating, screw, hermetic, semi hermetic. So different types are there of compressor. Okay, also I told you about the cooling towers. So cooling towers are used to cool the water coming out of the condensers. So there are some these so there are uh, multinational companies which are involved in manufacturing of these components. So last lecture I have showed you Alpha Laval's heat exchanger. So Alpha Laval is a very big company. It is one office is in Pimpri, Pune. Uh, Along with heat exchanger, they have their other components also. So today we'll see what are the types of this vapor compression refrigeration cycle. So before going to that point, let us understand this misconception about heat loss. Okay, so from your second year of mechanical engineering, you have been studying about heat loss, and you have been studying the what is meant by this. If I tell the diagram of heat engine, okay. So let us say it's a heat engine. So what heat engine does, it takes energy from the source. Suppose source is at a higher temperature, it takes the energy QH, then it does some useful work. Okay, then some amount of energy is released to sink, which is at temperature TL. Okay, so it releases QL amount of energy to sink. Now in this case, from like your last 2 years of engineering, you have been hearing that QL is nothing but heat loss. Okay, QL is nothing but heat loss. Okay, but the thing is, who decide that this is a heat loss? Okay, who decide that if it is a benefit or is it a loss? Okay, so we have designed a heat engine. So our objective is to do the work W. Okay, so whatever which is not contributing to it, we calling it as a heat loss, right? So it depends on our objective. तुमचं ऑब्जेक्टिव्ह काय आहे त्यानुसार तुमचं लॉस काय आहे ते ठरतं, राईट? जसं की आपण एखादा माणसाला आपण युजलेस म्हणतो. ओके, सो अ पर्सन इज युजलेस, सो ही इज युजलेस टू यू बिकॉज ही इज नॉट युजफुल फॉर एनी हेल्प. ओके, एखादा माणूस तुम्हाला मदत करत नसेल, तुमच्या संकट वेळी तुम्हाला मदत करत नसेल, ठीक आहे, किंवा तो काहीच काम करत नसेल, तर आपण काय म्हणतो, युजलेस आहे. ठीक आहे, पण हे कोणी ठरवलं? तर आपण आपला फायदा बघितला, आपल्या फायद्याचा हा माणूस आहे का? नाही आहे, तर आपण काय म्हणतो, युजलेस आहे. So, like in this case of heat engines or refrigerators, see this term heat loss, it depends on our objective. If I use this energy, okay, तर इथं सिंक नाहीये, ठीक आहे. आता इथं सिंक नाहीये, okay. Instead of sink, if I put again one more heat engine, अजून एक heat engine टाकलं ह्याच्यामध्ये, heat engine 2, then what happens? This is no longer heat loss. Understanding? So this will become input. Then again it will do some work W2. Then there will be again one heat loss. Okay, so that is again QL2. So this heat loss now reduces. So as long as your objective holds good, and that objective will define the heat loss. Okay, So why I'm telling you this, that because if you see an example of cold storage, okay, तर कोल्ड स्टोरेजमध्ये काय असतं, आतमध्ये सगळीकडे तुमच्या इव्हॅपोरेटर कॉइल्स पसरलेले असतात. सो दिज आर द इव्हॅपोरेटर कॉइल्स. आणि बाहेर कुठेतरी एक कंडेन्सर सेपरेट युनिट असतं कंडेन्सरचं. ठीक आहे. सो दिस इज अ कंडेन्सर. तर कंडेन्सर काय करत असते, तर ठराविक एनर्जी ॲटमॉस्फिअरमध्ये रिलीज करत असते. ठीक आहे. And we are calling this energy as loss. So this is a energy loss because we cannot recover that energy. So that is a loss to you. But if you can recover that loss, then that will be again a that won't be counted as a loss. Okay. So how they do that? So we are taking that energy and we are using for drying purpose. Okay. So if you take an example of our grapes. Okay. So what we do, grapes are dried and then we get a kishmish. Okay. So traditionally what they do, they put these grapes in one shade, एका शेड मध्ये ठेवतात. त्याला पहिला काय करतात, एका लिक्विड मधून भिजवून काढतात, त्यानंतर शेड मध्ये ठेवतात. शेड मध्ये 12 दिवस ते 14 दिवसात ते ड्राय होऊन निघतं. ठीक आहे. तर आता अशा अशा टेक्निक निघालेत की ज्यामध्ये एका दिवसात देखील ते आपल्याला ड्राय करता येतं. तर त्यातली एक टेक्निक अशी आहे की तुम्ही कोल्ड स्टोरेजची जी एनर्जी ऍटमॉस्फिअर मध्ये लॉस होते, एनर्जी लॉस होते, तीच एनर्जी तुम्ही वापरायची कशासाठी, तर ड्राइंग पर्पज साठी. सो दिस इज अ प्रोसेस ऑफ ड्राइंग. मग जे ड्राइंग झालेले आहे ग्रेप्स, ते मध्ये ते घेऊन तुम्ही परत कोल्ड स्टोरेज मध्ये थोडं मध्ये ग्रेडिंग करून त्याचं सॉर्टिंग करून कलर नुसार ते सगळं करून तुम्ही चांगल्या प्रतीचा माल, 1 नंबर माल, 2 नंबर माल, 3 नंबर माल, म्हणजे डिपेंड्स ऑन कलर. सो दॅट यू कॅन स्टोर इन द cold storage. Okay. So remember, it depends on the objective. So to whom we should call the heat loss. So if the objective is like to recover all the losses, so there are some waste heat recovery system you might have heard, which are installed in the thermal power stations. So in that case, what we are doing, we are restricting that heat loss. Okay. So always remember, uh, so there is a term which is famous nowadays, which is used widely, that is energy efficiency. In energy efficiency, what we are doing, we are restricting that energy losses. Okay. So in IC engine, that we know that efficiency of IC engine that lies between 30 to 40 degrees Celsius. Okay. Not 40, like it may be around 30%. So 30% is the maximum or near about the efficiency for IC engines. And we can see that there is a 70% heat loss. Okay. Now there are various methods to recover this loss. So we are using turbochargers, we are using superchargers. Okay. Then again, there are some methods in which this exhaust gases energy is stored in the phase change materials. So phase change materials, also called as PCM, these are also used to store this energy. Okay. So this is also very interesting topic, waste heat recovery. So you can search online and you will find very interesting projects. Okay. So that's one thing I wanted to clear. Now we'll move towards our topic. Okay. So last lecture, we have showed you, so vapor compression cycle on pH chart. pH chart stands for pressure and enthalpy. So on y-axis, we have pressure. On x-axis, we have enthalpy, and we have a pH chart here. So this is a curve. So this is a saturated liquid curve. And on this side, we have saturated vapor curve. So somewhere here at the apex, we have a critical point. So we have this curve, and inside that we can show that vapor compression cycle. So for example, in this case, it is showed by the red lines. Okay. So what you see here, so there are two pressures. So in BCC, there are two pressures are involved. So the higher pressure, this we called it as a condenser pressure. This is a condenser pressure, and the lower side, this is what we call it as a evaporator pressure. Evaporator pressure. Okay. So there are these two pressure values in VCC. Now see in this diagram what they are showing. If I take this as a point 1, let us say this is 2, this is 3, and this is 4. Okay. Now I'll ask you, what is the condition of refrigerant at point 1? Okay. What is the condition? So whether it is a liquid or is it a vapor or is it a mixture of liquid and vapor? Okay, so that you have to tell. Okay, understood my question? My question is, what is the condition of refrigerant at point 1? So this is the point 1 here, which is an inlet to the compression, or also we can call it as a exit of the evaporator. So at the exit of evaporator or the inlet of compressor, in this figure, what is the condition of the refrigerant? So there are some, I can give some hints. It can be liquid, it can be vapor, it can be liquid plus vapor. So we have to identify it. Okay, I have one answer. I'm waiting for others also. Okay. So seeing in the diagram, you have to identify what is the condition of refrigerant when it comes out of evaporator or before the compressor in this diagram. So only one answer I have. I will wait for others also. Okay, Akshay has given answer. Same answer he has given vapor. So vapor is correct answer, or more precisely, I will tell it is a dry saturated vapor. Okay. So at 1, the condition of refrigerant it is dry saturated vapor. Now why it is a dry saturated vapor? See on this line. So I'll erase these others. So if you take this line 1 to 4, on this line, this point if I take, so this point would be saturated liquid point. So liquid is being saturated and now it is starting to convert into vapor. So if we take any point in between this region, if I take this point will be wet mixture, that will be liquid plus vapor. So if I add more heat into it and it eventually comes at point 1, at that time all the dryness, all the this content of liquid will be vanished, and what we get is a get it as a dry vapor. Okay, then there is one more I have added here, dry saturated. So this is, as this is on this saturated vapor curve, so that will be dry saturated vapor. So condition of refrigerant at the exit of evaporator or the compressor, in this figure it is dry saturated vapor. Okay. Then moving on, so 1 to 2 is a compression process. So you have to tell what will be the condition of refrigerant at the point 2. Okay. So all the answers are there on the screen. You have to just closely examine it, and you have to tell what will the condition of refrigerant at point 2. Okay. So point 2 is the end of compression, or it is a inlet to the condenser. Yes, I have one answer here. So Pranil says it is a superheated vapor. So as I told you, all the answers are there on the screen. See on the right of this saturated vapor curve, we have a superheated vapor. So it is shown there. It is a superheated vapor. Whatever left of the saturated liquid curve, that is a subcooled liquid. Okay. So at point 2, what is happening? So point 2 is not on saturated vapor curve. It is just right of it. So whatever right of saturated vapor core, that we call it as a superheated. So it is a superheated, and that will be vapor. That is a superheated vapor. Now next thing is, so at 2 we are at the end of compression. So 2 to 3 is a isobaric heat rejection process. So that happens inside condenser. Now point 3 is the end of condenser. Okay, point 3 is the end of condenser, or it is a inlet to the expansion wall. Okay, so you have to tell by looking at the diagram what will be its condition. Okay, so I have one answer, saturated liquid. So Rohit says it will be saturated liquid. Yes, that is correct, because 3 lies on this curve. So what this curve, it is a saturated liquid curve. So that is why the point 3 will be saturated liquid. Okay, if it comes here, if I go a little bit further here, if I take this point at 3 dash, what will be its condition? So Pradel says it is a dry saturated liquid. So we cannot say it is a dry. Say liquid means it will be wet. So whenever liquid is fully converted into vapor, that time only we say it is a dry vapor. Okay. So we cannot say dry liquid. Dry means there is no liquid. Okay. So that term itself, it is a contradictory. So it will be simply saturated liquid at 0.3. Now my further question is, at the same pressure, if I cool the liquid to the 0.3 dash, what will be its condition? Okay, I will repeat the question. See, we have seen in the case of 2. Okay, so in the case of 2, what I asked you, the condition of refrigerant. Now, that refrigerant we have passed to the condenser, and it reaches to 0.3. So you are given the answer for 0.3, that condition of refrigerant at 0.3, it is a saturated liquid because it lies on this saturated liquid curve. Now my question is, if I further cool it at the same pressure to the 0.3 dash, what will be its condition? Okay, so Nishkalan says it will be liquid. Yes, it will be liquid, but more precise answer is given by Pranil, that will be subcooled liquid. So as I said, the answers are on the screen. So it will be subcooled liquid if it comes just left to the saturated liquid curve. Okay, so 3 dash will be subcooled liquid. Then what happens? So from 3, we pass it through the expansion wall. It comes to the point 4. Okay, so 4 is the end of the expansion wall, or we can say it is the entry to the evaporator. Now, by looking at the diagram, you have to tell that what will be the condition of refrigerant at point 4. So see, point 4 is neither on saturated liquid curve nor on saturated vapor curve. It is in between it. So what will the condition at point 4? So again, the answers are there on the screen. You have to determine what will be the condition of refrigerant at point 4. Meanwhile, I'll write here answer. So this will be point 3 will be saturated liquid. 3 dash will be subcooled liquid. Okay, now my question is, what will the condition at point 4? Okay, so watch closely the diagram. The answer is there on the screen. Okay, I have two answers. Rohit says it will be liquid plus vapor with some dryness fraction. Yes, that is the correct answer. Pranit says saturated liquid and vapor. See, it is like correct. It will be like saturated because saturated liquid, if you add latent heat into it, it will try to convert into vapor, right? So yes, it is at saturation pressure only, but we should not. It is not generally mentioned that it is a saturated liquid plus vapor. Simply we can say that at 4 we have liquid plus vapor, so it is mentioned there, liquid vapor mixture. Saturated point comes here at 2 points only, saturated liquid point and saturated vapor point. When we are in between, that will be a wet mixture. Okay, so in between it is a wet mixture, so at point 4 we have a liquid plus vapor mixture with some dryness fraction, as rightly mentioned by Rohit. So at point 4, that will be straight away you can write it as a wet mixture. So point 4, it is a wet mixture. What is happening there? If it is was point 4 dash, so point 4 dash ला काय आहे या केसमध्ये इट इज अ सॅच्युरेटेड लिक्विड. जसं जसं मी त्याच्यामध्ये हीट ऍड करत जाणार आहे, इट कम्स टू पॉइंट 4. नाउ व्हॉट इज हॅपनिंग हियर? Some part of liquid is removed. Okay, some part of liquid is removed. So point at point 4 dash, if I take the dryness fraction, okay, so that will be 0. Okay, so dryness fraction means amount of dryness or amount of presence of vapor into the mixture. So at that time x will be 0. Now as you heat that mixture at point 4, x will have some value. Let us say x is equal to, let us say it will be 0.2. Okay, if you further heat that mixture, if you further supply the latent heat, it will reach to 0.1. Now at 0.1, what is happening? At that time x is equal to 1. That means that mixture is completely now dry vapor. Okay, so this is how the cycle works. If you simply remember this pH curve, and then you remember that left part is subcooled, right part is superheated, in between it is a liquid vapor mixture, your idea about various processes will be more clear. Okay, so those who did not understand this figure or any questions, if you have, you ask now, because as we move further in this topic, it will be very difficult if you do not understand these processes. Okay, so I'll repeat again. Point 1, it is a dry saturated vapor. Point 2, it is a superheated vapor because it is left to the saturated liquid vapor curve. Then at point 3, it is a saturated liquid because it lies on saturated vapor curve. Then 4 is in between saturated liquid and in between saturated vapor. That is why it will have some dryness fraction. Okay, so at point 4 we have liquid plus vapor mixture. Right. So this is the idea about the VCC on pH chart. We'll see now various processes involved in it. So types of vapor compression cycles. So there are 5 types. First is dry saturated vapor after compression, wet vapor after compression, superheated vapor after compression, superheated vapor before compression, undercooling and subcooling of the refrigerant. Okay, so we'll see one by one. So first in it is dry saturated vapor after compression. Okay, so I'll draw the diagrams. So first I will draw the temperature, or first I will draw simply that pH chart, pressure versus enthalpy. Okay, so this pressure, it will be absolute pressure and this will be kilojoule per kg. So enthalpy, as I taken the small, it will be kilojoule per kg. I hope you all know that if I take capital H, so that is also enthalpy, but its unit will be kilojoule. If I take small h, that means it is kilojoule per kg. Okay, so that is the with symbol convention it is used. So if I draw the pH chart, okay, so I will draw it. So two diagrams are there on your screen. First is a pH diagram. Second is a TS diagram. So you see in this diagram, the processes are same 1 to 2. It is isentropic compression. So it is a compression. So as it is an isentropic compression, isentropic means entropy remains constant. So we have shown in that TS diagram. So 1 to 2 process, as you see, the entropy remains constant. So at this point, S1 will be equal to S2. Now 2 to 3, it is a isobaric heat rejection process in condenser. So 2 to 3, it is condenser. Okay. So as it is a isobaric process, we have shown it as a horizontal line. Now 3 to 4, it is a what it is isenthalpic process. So it is a constant enthalpy process. That is why we are shown here straight line. So enthalpy at point 3 will be equal to enthalpy at point 4. 4 to 1, as we know, it is a evaporation process. So this is the main part of our system which extract the heat from the space. It is an evaporator. So that also occurs at constant pressure. That is why we are shown it as a horizontal line. Okay. So I want you to draw these two diagrams. Then we'll calculate how to get the COP. So in this first case, that is a dry saturated vapor after compression, as the name suggests. So what the name is suggesting you, there will be a dry saturated vapor after compression. So after compression means that will be point 2. So point 2 will be dry saturated vapor. That means it will lie on this saturated vapor curve. So that is the meaning of it. So point 2 will be on dry saturated, saturated vapor curve. So you can get the idea from the name itself. So you don't have to mug up these things, right? So if you have understood our last point, then you can easily draw the diagrams for these types of VCCs. So first type we are dealing with, it is dry saturated vapor after compression. So as the name suggests, at the end of compression we have a dry saturated vapor. So easily from diagram also you can get that. So point 2 is dry saturated vapor. Okay, so we have four processes. 1 to 2, it is isentropic compression of vapor to dry saturated vapor by compression. So in this case, that compression work WC will be equal to H2 minus H1. Now 2 to 3 is constant pressure and temperature heat rejection. In that case, vapor is converted to liquid. Process 3 to 4, it is isenthalpic expansion by throttle or expansion valve. Process 4 to 1, it is a constant pressure and temperature, heat absorption by refrigerant. In that case, that liquid vapor mixture, the dryness fraction is increasing. Okay, so the liquid fraction is reducing, that means the dryness fraction is increasing in evaporator coils. So heat absorbed, or we can say refrigeration effect. So refrigeration effect, so QL is equal to what? It will be equal to, it will be equal to H1 minus H4. Okay, so only these two quantities we need to calculate COP. So COP will be equal to QL divided by work required. So in this case, work of compressor, that will be equal to H1 minus H4, that is a refrigeration effect, divided by H2 minus H1. Right? Now, looking at the diagram, you can easily say that H3 is equal to H4. So here I have written it, H3 is equal to H4. Now you can see here H3 is nothing but what it will be? It will be HF3. Okay, it will be HF3. So HF, these are the enthalpies which are related to saturated liquid. If I take Hg, Hg is nothing but enthalpy of saturated vapor. Saturated vapor. Okay. So if I want to know the enthalpy at point 4, simply I have to calculate what will be the enthalpy of saturated liquid at condenser pressure. So here we have condenser pressure, and here we have evaporator pressure. So values will be given to you in numericals. So at condenser pressure, what is the HF value, what is the Hg value? At the evaporator pressure, what will be the HF value, what will be the Hg value? This value will be directly given to you. So so in your university exams, these values are directly given. I have not seen any question where you have to refer to the psychrometric chart or a refrigerant property chart, and then you have to take the values from the chart. But still we'll use that chart when we'll solve this example, because in industries, these charts and these table values will be used. They don't give you the directly the table values. Okay, so there is a difference between your university exams and real life examples. So, okay, so when we'll solve the examples, I will give the table also, the ready values, but we will make use of that refrigerant chart also. Okay, so this is our first type, which is a dry saturated vapor after compression. Next, we'll see is a superheated vapor after compression. So I'll draw the diagrams again. So this is a pH. Okay, this is a TS. So as the name suggests, you might have already imagined it. So condition of refrigerant at the end of compression, that is a superheated vapor. So like we have studied in last example, it will be same here. So let me draw the pH curve. So this will be saturated liquid curve. This will be saturated vapor curve. Then I will draw that diagram again. Okay, so this will be point 1, 2. Let us say this is a point 2 dash. This is a 3 and this is 4. So 1 to 2, you know, isentropic compression. 2 to 3, isobaric heat rejection. 3 to 4, constant enthalpy expansion. 4 to 1, it is isobaric heat absorption. Okay. Likewise, I will draw the TS diagram also. Okay. So again, 1, 2, this will be 2 dash 3 and 4. So 1 to 2 compression, 2 to 3 heat rejection, 3 to 4 constant enthalpy expansion, 4 to 1 again heat absorption. So heat is absorbed QL, it is rejected QH, and here some work is required, that is a compressor work. So this is the diagram for this condition, superheated vapor after compression. So as the name suggests, condition of refrigerant at the end of compression. So end of compression is nothing but point 2, that is a superheated vapor. Okay. So what is the superheating? Superheating is the sensible heating of refrigerant vapor at constant pressure in the evaporator to a temperature more than the temperature of saturation corresponding to the evaporator pressure. Okay, superheat occurs in evaporator to protect the compressor. So I think this diagram uh, is correct. Yes, it is correct. So if you take temperature at point 2 as a T2, temperature at point 2 dash as T2 dash. So if I take this different T2 minus T2 dash, this is generally called as degree of superheat. Okay. What is T2 dash? T2 dash is nothing but saturation temperature at condenser pressure, and T2 is the superheated temperature. So if I take T2 minus T2 dash, that will be degree of superheat. So while solving the problem, first you have to know the S1. Okay, so this is isentropic compression. So S1 will be equal to S2. Then you can calculate the T2. How you can calculate the T2? So S2 will be equal to Sg2. So entropy of saturated vapor at point 2 dash plus Cp ln T2 by T2 dash. So this is the formula which is used to calculate entropy of superheated vapor. From this equation, so here Sg2 is known, T2 dash is known, and you can easily calculate the T2. So that will be temperature of superheated vapor, right? So in this case also that formula will remain the same. So COP will be equal to refrigeration effect divided by work required. So here it will be H1. So H1 minus H4 divided by compressor work, that will be H2 minus H1. Okay, so in this case also this H4 will be equal to H3, which will be equal to HF3. Okay, HF stands for enthalpy of saturated liquid at point 3. Okay, so this is our second type. We'll move to the next. So if you have any questions, you can ask. But I think this is very straightforward. So by looking at name, we can directly draw the diagrams. Okay, so next is superheated vapor before compression. So I hope many of you already have imagined it. So how that diagram will be. So at the entry of compressor, that refrigerant will be superheated. So first I will draw the pH diagram. So pressure versus enthalpy. Okay, so this will be temperature versus entropy diagram. Here it will be point 1. It will be point 1. This will be isentropic compression. Point 2. Let us say this is point 2 dash. This will be point 3. This will be point 4. Let us say this is a point 1 dash. Okay. Okay. So on pH chart, so Anna sir, I will mark your attendance. Don't worry. So on pH chart, I have drawn this diagram. See here what is they are saying, superheated vapor before compression. Before compression means that will be end of evaporator, so that will be point 1. So before compression, that refrigerant is superheated. So is it true? So it is true in this diagram because this is a superheated saturated vapor curve. On right of it, everything is superheated. So condition at point 1, that will be superheated vapor. Okay. So 1 to 2 again, that will be isentropic compression. 2 to 3, that will be isobaric heat rejection. 3 will be end of condenser. 3 to 4 will be constant enthalpy expansion. 4 will be entry to the evaporator. So this is the evaporator. This is a condenser. 4 to 1 will be isobaric heat extraction process. Okay. Here similarly, here also we can write it as, so this will be 1, this will be 2. Then let us say this point is 2 dash, this point will be 3, in this point it will be 4. So 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay. So as the name suggests, superheated vapor before compression, that means before compression. So before compression, that means we point 1. Point 1 is superheated vapor. Okay, so COP, that formula remains same everywhere. So COP will be again H1 minus H4 divided by work required, that is a compressor work, that is nothing but H2 minus H1. Okay, so again that H4 will be equal to H3 because it is a constant enthalpy process, 3 to 4. So that will be again equal to HF3. But see here how to calculate enthalpy at point 1 and how to calculate enthalpy at point 2. Okay, so that formula it is there. So if I want to calculate H1, so H1 I will write equal to, so this will be some quantity in addition to enthalpy of saturated vapor. Okay, so we have saturated vapor at point 1 dash, and then if I add some more energy to it, I will get 1. So 1 will be some quantity of Hg1 dash. Why I have taken Hg? Hg means enthalpy at saturated vapor. So that is why I have taken Hg at point 1 dash plus some energy. So what will be that some energy? That will be Cp delta T. So Cp into delta T means T1 minus T1 dash. So that will be the enthalpy at H1. Okay. So by looking at diagram also you can get the idea. So if you see here 1 dash, 1 and 1 dash, you see there is some difference of energy. Okay, so this difference of energy is nothing but Cp delta T. So that will be Cp into T1 minus T1 dash. Okay, so enthalpy at point 1 will be enthalpy at point 1 dash plus Cp delta T. So that is nothing but H1 is equal to Hg1 dash plus Cp into in bracket T1 minus T1 dash. Similarly, I can calculate for H2 also. So only the notations will change. So H2 will be equal to Hg2 dash plus Cp into, so what will be here? Delta T. Delta T will be T2 minus T2 dash. So thus we can calculate the enthalpy values H1 and H2. So further more question arises how to calculate this T2 and T1. So this you can calculate from the assuming that compression process is isentropy, that entropy remains constant during 1 to 2. Okay, so that will be again different scenario. So when solving the examples, we will come to know how we are calculating this enthalpy values. Okay, So to calculate the enthalpy values at H1 and H2, we need temperature value at 1 and 2. That temperature value we can calculate from assuming that compression process is isentropic. Okay, so this is about this thing. And this is the last type, that is undercooling or subcooling of refrigerant. So by looking at the name, many of you might have got the idea how the diagram will be. So in this case, that refrigerant at the end of condenser, it is subcooled. Subcooled means it will lie on left of saturated liquid curve. Okay, so I will draw the diagram. So this is a pressure versus enthalpy. This is temperature versus entropy. So remember, this is a small s. Okay, its unit will be kilojoule per kg Kelvin. Okay, if I take capital S, so that will be kilojoule per Kelvin only. Okay, if I take small s, its unit will be kilojoule per kg Kelvin. So it is temperature versus specific entropy. Here it is pressure versus specific enthalpy. Right? Now I will calculate the, I will draw the diagram for this. Okay. So in this case, all the other processes will be same. So if I take point 1, there will be isentropic compression. Then it will pass through the condenser. So at the end of condenser, there will be subcooling. So the temperature will reduce further up to 0.3. So then it will pass through the expansion wall. It will come to 0.4. Then it will pass to 0.1. So 1, 2, 3, and 4. So watch closely. There are two processes here, like refrigerant is superheated at 0.2, and second is like refrigerant is subcooled at 0.3. So what is happening here? 1 to 2, as we know, it is isentropic compression. At the point 2, we have superheated vapor. It is passed through the condenser. Okay, so phase change takes place. It reaches to a point 3 dash, which is a saturated liquid point. So if I cool further saturated liquid, then it will be subcooled. So I have point 3, which is a subcooled. Then it will pass through the expansion wall. It will come to the point 4. So that will be entry of evaporator. It will pass through the evaporator. I will reach to the point 1. So this is how this cycle repeats. I will draw the TS diagram also. So this will be point 1, 2, let us say this is point 2 dash. Then this is will be point 3 dash. This will be our point 3. This will be point 4. So TS diagram is little bit different here. So 1 to 2 compression, 2 to 3 condensation, 3 to 4 expansion, 4 to 1 it is a heat extraction. So this is the diagram for subcooling of refrigerant. So as the name suggests, there is a subcooling of refrigerant after condenser. So after condenser, we are reducing its temperature below its saturation temperature. So remember these terms, saturation pressure and saturation temperature. So at point 3 dash, so if you come here point 3 dash, what you see, it is a saturation temperature. So if I reduce the temperature below it, I would get the value 3, which is a subcooled refrigerant. Okay. So in this case also, that COP formula, if I take, so that will be H1 minus H4 divided by H2 minus H1. Okay. And that H4 will be again equal to H3. Now in this case, I cannot take H3 is HF3 because it is not lying on saturated liquid curve. So in this case, H4 is equal to H3. How to calculate enthalpy at point 3? So enthalpy at point 3 H3 will be less than enthalpy at point 3 dash. Agree? So if you look at the diagram here, this will be enthalpy at point 3 and this will be enthalpy at point 3 dash. See, there is a this gap in between them. Okay, so this gap again, it will be Cp delta T. So this will be Cp into Tt3 dash because it is higher minus T3. Okay, so there is this energy gap. So we can say that enthalpy at point H3 will be equal to enthalpy at point 3 dash. So 3 dash, it lies on saturated liquid line. So that will be HF 3 dash minus Cp delta T. So here it will be T3 dash minus T3. So if you calculate H3, that will be equal to H4, that you can put in the COP formula and you can get the value of coefficient of performance of a refrigerator which is operating on this cycle. Okay, so I'll just quickly take the review of what we have seen today. So we started with VCC on pH chart. I explained, use some processes. I tried to keep it interactive because this was very important point. After this, we saw some processes in the vapor compression cycle. So first was dry saturated vapor after compression. That means after compression, that is point 2, that should be dry saturated. That means it should lie on saturated vapor curve. Then next was superheated vapor after compression. That means after compression, so at point 2, that vapor should be superheated vapor. That means it should lie on right of saturated vapor curve. Third was superheated vapor before compression. So before compression means end of evaporator. So at the end of evaporator, that it should be superheated. Okay. So why it is important to have superheated vapor before compression? Because compressor works on only vapors or gases. If there is any minute fraction of liquid, then that compressor damages. Okay, so it is always advisable to have superheated vapor before compression. But in this case, what happens? The net effect is COP reduces because of this superheating. And the last was undercooling and subcooling of refrigerant. So in this case, what we are doing, we are cooling the refrigerator at the end of condenser below its saturation temperature. So we get that 0.3. So it is very good. It increases the life of the expansion wall. So subcooling increases the COP as well as it increases the life of the expansion wall. So these were 5 types of VCC. I hope I have cleared. I have cleared your doubts. Also, I have explained with more clarity. Once you start solving the examples, your concepts will be more clear. Okay. So, any doubts? Okay. Takle is saying no doubt. Takle is a very intelligent student. He's saying no doubt. So you should have doubts. Okay. No doubts means you are not thinking. So Rohit is saying third process. Third process means which one? Superheated vapor after compression. Wet vapor before compression. So yes, that I have skipped it. I think superheated vapor before compression. Okay, okay, okay. So this one, right? Okay, okay, okay. So he's saying that please explain. Okay. So see here, as the name suggests, so there should be superheated vapor before compression. So before compression means what? At point one. So 1 to 2 is a compression process. So if I come to point one, that will be before compression, two will be after compression. So that vapor should be, so that condition of refrigerant should be superheated vapor. So what we are doing in this case actually, so at the end of evaporator, so at the starting of evaporator, what we have here it is liquid plus vapor. At this liquid plus vapor refrigerant passes through evaporator coils, it gets the latent heat from the space. Okay, it gets the latent heat from the space. Because of this, it is first converted into saturated vapor. Okay, now it if it further gets heat, okay, if it further gets heat from the space, if further heat is transferred to this refrigerant, so what will happen in that case? Its temperature will increase. It so at the point 1 dash we have temperature, here we have saturated saturation temperature at evaporator pressure. Okay, so 1 dash is saturation temperature at evaporator pressure. If I transfer more heat to that vapor, what will happen? Its temperature will increase to zero point 0.1. Okay, so it will shift right to the saturated vapor curve, that will be superheated vapor. So that is why it is saying that before compression, superheated vapor. So that condition at 0.1 here, it will be saturated vapor. Okay, and it is always advisable that it should be superheated to increase the lifespan of the compressor. So compressor cannot handle liquids, that is why it should be superheated vapor. Okay, so in that case COP we are calculating by using the same formula, but in this case H1 and H2, to calculate H1 and H2 we have to use these two formulas. Yes. So Takle, you should have doubts. Okay. Next time I want you to ask doubts. So okay, okay. So okay. So today we'll stop here. Just let me take the attendance quickly. Okay. So your attendance I have taken. So thank you for being here. Please be there in next lecture because we are going to solve numericals. Okay. So thank you. Bye. And yes, Rohit, thank you to you also.